my name is Herschel, I'm a particle physicist, and today I'd like to tell you all about my subject and what makes it such an exciting area of research. Particle physics studies the smallest, most fundamental particles that make up the world around us. You may remember from school that the world is made of atoms, and atoms are made of protons, neutrons, and electrons. But that's just the beginning of the story. Over the past 100 years, we've discovered hundreds of new particles, each no less fundamental than the proton and neutron. In fact, we know today that most of those new particles, and indeed also the proton and neutron, are made of smaller particles called quarks. And it is the quarks and the electron and a few other particles that actually seem to make up our world. Let me highlight here the photon, which is a particle that makes up light, and the Higgs boson, discovered recently in 2012. It's to do with, relates to how particles get mass, and it immediately won the 2013 Nobel Prize. We study these particles by building big machines called particle accelerators that accelerate particles up to very high energies, close to the speed of light, and then collide them together. The largest one is at CERN, on the border between France and Switzerland. It's 20 miles in circumference. It accelerates particles up to very high energies and then collides them together. At the point where they collide, we build these huge detectors that measure what comes out of the collision. The point isn't to break apart the particles that we're colliding. Actually, Einstein's famous equation E equals mc squared tells you that with sufficiently high energy, you can make brand new particles, and that's what happens here. Now, my job as a particle theorist is to calculate and predict what happens in these collisions. But making these calculations is really, really difficult. One of the most difficult aspects is calculating things called integrals that look like this. And these integrals are really, really hard. Now, some of you might be convinced just by looking at it that it's difficult. For the more mathematically inclined, let me point out that d here is the number of space-time dimensions, which is 4. There are 2 d's here, so that's an 8-dimensional integral, and that's very difficult, particularly when the thing inside is often infinite. During my PhD, I wrote a computer program to solve these kinds of integrals. And by running it on a national supercomputer, we solved a big class of integrals, which we publish in this paper here. The results were 20 gigabytes in size, which is more than the entire human genome. And you may know that can fill an entire bookcase. Using those 20 gigabytes of results, we calculated the world's first ever high precision calculation for a 3-particle production process. Specifically, we calculated at that collider at CERN, how often will you produce 3 photons? Remember, a photon is a particle of light. So this graph shows here, in gray is what they actually measure at the experiment, and in various colors are the predictions. So in green is the low precision prediction, which you could do almost with pencil and paper. In blue is a medium precision prediction, which was done about 25 years ago. And in red is our high precision prediction done with the help of those 20 gigabytes of data. And you can see that the high precision prediction agrees with the experiment. And the fact that it took 25 years to go from the medium precision to the high precision gives you an idea of just how difficult these calculations are. Now, these days, I'm working on similar calculations, but now involving these exotic particles over here, including that Nobel Prize-winning Higgs boson. Now, these particles are really, really heavy, and that makes the calculations even more difficult. But hopefully, we can carry the calculation through and then make some predictions about them, compare with the experiment, and thereby get a better understanding of how these particles work. And maybe, if the predictions disagree with the experiment, then maybe we'll even get the first hints of some new particles waiting to be discovered. Now, personally, I think that this kind of pure, fundamental, basic research, curiosity-driven research, is worthwhile in its own right and really exciting, and I hope that you agree too. But beyond the sort of pure joy of knowing how the world works, there are also practical applications. Sometimes they take a while. I mean, when the electron up there was discovered 2 centuries ago, no one imagined that 2 centuries later we'd be using it for TVs and phones and computers and everything else. So I can't possibly tell you what the Higgs boson might be used for in 2 centuries. But in the meantime, let me highlight that there are actually 30,000 particle accelerators all around the world, smaller than ours, of course. Most of them are found actually in places like hospitals where they're used for treating cancer. The detector technology that we developed that are used that the particle physicists developed at colliders in order to study what comes out of collisions. The same detector technology is used for medical imaging and even for national security, for scanning, for example, the contents of shipping containers. And finally, of course, the World Wide Web was famously invented at CERN to help particle physicists collaborate. Here's the inventor of the web sitting at his desk at CERN, and on the screen is the world's first ever website. In summary, particle physics studies the smallest, most fundamental particles that make up the world around us. We do this by colliding them at very high energies and seeing what comes out. My job as a theorist is to calculate and predict what comes out of those collisions. And by comparing against experiments, we can get a better idea of how the world works and perhaps even discover new particles that are around the corner. Thanks very much.